Welcome back, everyone. We are officially at part 5 of our 6-part explainer series, diving into the Merg-E language specification. Today, we're going to focus on a really specific, kind of fascinating cluster of the architecture, parts 16 through 19. If you've been following along, you already know Merg-E does not do things the standard way. It is a strictly opinionated, least authority, domain-specific language built from the ground up for Web 3.0. Today, we're unpacking exactly how it handles system inputs, runtime memory accounting, and its rather unique compile-time numeric type system. Let's get right into it.
Here's our roadmap for this explainer. First up, Part 16, covering async functions and vaultfs. Then we'll hit Part 17 on RAM points and quota membranes. After that, Part 18, looking at literal operators and numbers. And finally, we'll wrap up with Part 19, the virtual numeric type system.
All right, starting off with Part 16, async functions and vaultfs.
So Merg-E has some incredibly strict rules when it comes to system arguments. Unlike most languages we're used to working with, it completely cuts off direct memory access to argv. Why? Well, to fundamentally prevent injection vulnerabilities. It's a really smart move. Instead of direct access, it safely maps those arguments straight into the scope-directed acyclic graph. Specifically, you'll find them under scope.arguments. On top of that, it enforces a really rigid -option-val syntax for parameter pairs. Oh, and if you're defining an absolute path, it absolutely must start with a /. In fact, if that designated path doesn't actually exist on the system, the Merg-E interpreter will just flat out refuse to start. This perfectly illustrates the language's total security-first mindset. By denying direct memory access and forcing the entire environment into this strictly controlled, explicitly defined scope structure, Merg-E guarantees that no hidden or malformed inputs can just slip past the runtime. You literally only get exactly what you explicitly permit through the language bindings. No surprises, no backdoors.
Moving right along to Part 17, RAM points and quota membranes.
Now, this is where things get really cool. RAM points act as this transparent runtime cost communication mechanism. What that means in practice is, in Merg-E, every single scalar type has to be able to communicate its exact cost right at runtime. Plus, every membrane, which acts as a security boundary or proxy in Merg-E, must also be able to dynamically report any additional processing cost it incurs for handling those types. It's basically a fully transparent built-in cost calculation tool.
You know, Merg-E heavily relies on what the spec calls thin abstractions, and this directly solves some massive real-world developer headaches. Think untraceable memory leaks. Instead of just burying the computational weight of your data structures under layers of automated garbage collection or hidden memory managers, Merg-E just exposes the whole thing. As a programmer, you can see the exact RAM points and quota limits your code is consuming. It makes performance and memory ceilings completely auditable, right there in front of you.
Okay, let's pivot to Part 18. Literal operators and numbers.
While this part of the specification is definitely brief, it is absolutely crucial. It standardizes exactly how the compiler interprets literal mathematical operators before executing any deeper type resolution. Specifically, it lays down the groundwork needed to accurately represent exact rational and complex numerical types. So when you're writing out a complex mathematical equation, you can be absolutely sure the merging compiler parses those literal tokens with total precision right before applying any of its dimensional logic.
And that brings us to Part 19, the virtual numeric type system.
So during the initial line parsing phase, the compiler brings in an array of virtual numeric types to absolutely guarantee that your arithmetic operations won't overflow. Looking at the breakdown here, we have whole numbers, that's v whole, stepping by 1 bit all the way up to 32,768 bits. Integers, or vint, do the exact same thing. Then we step up to integer complex numbers and rational numbers, scaling all the way up to 65,536 bits. And finally, we have rational complex numbers, the vcrat type, which step up by 4 bits at a time.
And get this, the maximum upper bound for those rational complex numbers, it reaches a massive 131,072 bits. Think about that scale for a second. Merg-E utilizes these absolutely gigantic virtual types at compile time to mathematically guarantee that when two variables interact, the intermediate value has an exact, perfectly sized bucket to sit in. It completely safely prevents arbitrary overflow errors.
But don't worry, your compiled code isn't going to be dragging around 100,000-bit numbers at runtime. That would be a nightmare. These virtual types have a single expression resolve time.
They literally only exist momentarily at compile time to execute that mathematical validation. Once they've done their job, they instantly fold right back down into strict power-of-2 runtime bit-width types. It's just a highly structured approach to generic integer programming.
So let's recap what we've covered. We've mapped out how Merg-E securely locks down system arguments. We've seen exactly how it exposes those hidden memory costs through RAM points, and we've unpacked the sheer scale of its compile-time virtual numeric types. But this brings us to a pretty compelling question for our next explainer. With all these architectural pieces finally in place, what final dimensional constraints and physical data types remain to actually complete the Merg-E puzzle? Join us for Part 6, the final installment of this series, where we are going to bring this whole thing together. Thanks so much for learning with me today, and I'll catch you in the next one.